Okay, this is uh, about our number system. Our number system is a base 10 system, which means, okay, so that word base, that's base in the sense of an exponent. So, uh, oh, go away. So, for exponents, it works like, oh, that was cool. It works like this. So, this is the base. Oh, yeah, base. And this is the exponent. Exponent. Ah. Oops. So, whatever the base is, that's the number that gets repeated in the subsequent multiplication, and the exponent is the number of times that it gets repeated. So 10 to the 6th power would be that base multiplied by itself 6 times. Two, three, four, 5, 6 equals, I'll just add 6 zeros here. That's the cool thing about 10 in our number system. You don't have to really think, you just add a 0, or a square, I guess, comma every third 0, so it's a million. Okay, cool. So when I say our number system is a base 10 system, I mean base in the sense that it's used here in exponential arithmetic. Is this a recording? Okay, erase everything. So what that means is that every place in a number is some power of 10. So let's say I have 137. Each of these places is some power of 10. This is 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, and so on. You can see the pattern. It's always 10 in the base, and the exponent when you go left is just one more than whatever the exponent was to the right. So this becomes 5 times 10 to the fourth plus 1 times 10 to the third plus 3 times 10 to the second plus 7 times 10 to the first. And that becomes, it becomes just what is written above, of course. So, the same thing works in the other direction. So now we hit our decimal point, and if we continue to do... Oh, you know what? I am so sorry I misled you. It starts at 0, 1, 2, 3. I knew I was doing something wrong. Oh. I can do this better. 10 to the first, 10 to the second, 10 to the third. I totally misled you. these are the correct exponents. Because the thing is, do more on this right here. To the negative 1, 10 to the negative 2, 10 to the negative 3. The thing is that I will finish that thought once I've written this. The thing is that when you go up in the exponents, you multiply 10 times the previous thing, and when you go down, you divide by 10 from the previous thing. So let's say I start here at 1, which the exponent is 0, which is true for any number to the raised to the 0th power. This number raised to the 0th power equals 1. Doesn't matter what the base is. If the exponent is 0, the result is always 1. And that's because of the way this works here. So let's start with 10 to the first power, because that's, at least in my mind, that's the most obvious thing. 10 to the first power, so 10 times itself 1, I mean, it's just 10. There's just one of them. So if I go up to 10 to the second power, I multiply another 10. And then if I go 10 to the third power, I multiply by another 10. And if I did 10 to the fourth power, I would multiply by yet another 10. Oh, I put the comma in the wrong place, I'm sorry. My handwriting is pretty bad. You must bear with me. I mean, you don't have to, but I hope you will. Yeah, so as you go up, and this up and down is, again, the exponent. As the exponent goes up, the result is whatever the result for the previous exponent was times 10, or times the base, whatever the base is. And as the exponent number goes down, the result is whatever the previous result was divided by whatever the base is. So that's the way exponents work. So that's why anything to the 0th power is always 1, because when you raise anything to the first power, it's always just itself. So I'll use this random big number again. Raised to the first power, that's always itself. And then when you go down in exponents, so 1 then to 0, I divide this result by whatever the base is. So that's always itself in this case of going from exponent 1 to exponent 0. You're always dividing whatever the base is by itself, and you always will get 1 consequently. 7 raised to the first power is 7. 7 raised to the 0th power is... So I divide the previous result by the base. 7 divided by 7, that's 1. Yeah, I'm probably beating a dead horse here. It's a concept that once you get it, once I got it, it's obvious to me, but like before I got it, it was very abstract, so I'm just trying to reinforce it. But anyway, so the ones place in our number system, that's 10 to the 0th power, and as you go left, whatever the digit is, it's always that digit times the 10 to the appropriate exponent, which is always increasing by 1 as you go left, and then as you go right, it's the same, you just are decreasing, and you can go into the negatives. -2. -10 to the -3rd. So that would be, yeah, and you see there's a relationship here, like 10 to the 1st is 10, 10 to the -1st is 1 over 10, 10 to the 2nd is 100, 10 to the -2nd is 1 over 100, 10 to the 3rd is 1,000, 10 to the -3rd is 1 over 1,000. So these line up. It's just that instead of multiplying, you're dividing, basically, as I said before. So instead of it just being 100, it's 1 over 100. So this 8, well, I'll start with the 7. So 7 times 10 to the -1st is 7 times 1 over 10 equals 7 tenths equals 0.7. Yeah. Because when you multiply a whole number times a fraction, you just multiply that whole number times the numerator and leave the denominator as it is. So that's what this became. And just expressing it as a decimal here, which is what the original form was, just to go full circle. But the point is, yeah, these are tenths. This is the tenth. This is the tens place. This is the tenths place. This is the hundreds place. This is the hundredths place. So whatever this number is, times 1 over 100. Yeah. So now I'm gonna, oops, that's not what I want. I want to erase it. Oh, I can do this. Delete everything. Erase all, yes. So, hey. Didn't do it. That's alright. I can do it manually. So back to finding 20% of something, bearing all of this in mind. I should, I'm gonna undo that actually, because that's good to have. Yeah, I'll get rid of this, but that I'll leave over there as a reference. So 20%, a percent is always a fraction, that number over 100. Like 57% is just 57 over 100. That's just what percent means. It means whatever the number is divided by 100. So 20% is 20 over 100. And so let's say the price of the meal was this. So I want to find, oh, how do you do a dollar sign? Okay, like that, right? I want to find 20% of this. So 20%, 20% of this is, I'm screwing this up. 20% percent of 19.17 equals 20 over 100 times 1917. So because we have a base 10 number system, the easiest way for me personally to conceptualize this is to make this fraction, if I can, some form of dealing with base 10. And I can do that because I can reduce this fraction. 20 and 100 can both be reduced by 10. So if I divide both of these numbers by 10, I'll get a simplified fraction that has the same value, because the important thing with fractions is not the numbers themselves, it's the relationship between them. The point of a fraction is it's like a I'm trying to think if there's like a better way that I can say that. But I don't think currently I have one. The point of the fraction is the relationship between the numerator and the denominator. You can make these two numbers whatever you want as long as the relationship between them mathematically remains the same. So that's what I mean by that basically is, if I can multiply both of these numbers by 17, I just arbitrarily choose the number 17. So that would be 2 times 17 is 34, and 10 times 17 is 170. These numbers are very different, but the relationship between them is the same. I know it is because I multiplied both the numerator and the denominator by the same value. That's how I know the relationship is the same. So I know that the value of the fraction is the same. And if I were to divide both the numerator and the denominator by the same number, I know again that the relationship between them is the same mathematically. And that's the important part when it comes to fractions. So that's why I'm able to turn this 20 over 100 into a 2 over 10, because I divided them, both the numerator and the denominator, by the same value, 10. And I like it being in this form because dividing and multiplying by 10 works well with our base 10 number system, because as I multiply by 10, I go up in exponent, and as I divide by 10, I go down in exponent. So, and as I go up in exponent and down in exponent, that means I'm changing places in our number system again, because again, this is, let's do each of these places. The ones place, that's where I should always start. That's 10 to the 0th power, 10 to the 1 power, 10 to the 2nd power, 10 to the negative 1 power, 10 to the negative 2 power. So as I go up in exponent, I go left in placement in the number, and as I go right in as I go down in exponent, I go right in the number. So here I'm dividing by 10. That means I'm going down 1 in terms of exponent. So going down 1 means every number here gets shifted to the right, because this right now is 10 to the 0, this is 10 to the 1, this is 10 to the negative 1, this is 10 to the negative 2. That's what these four numbers, that's what these four digits are and represent in their current placements in this number. I multiply this 9 by 10 to the 0th power, and I add that to 1 times 10 to the first power, and I add that to 1 times 10 to the negative first power, and I add that to 7 times 10 to the negative second power. When I add all that together, I get the value of this number. Now when I divide by 10, when I divide this number by 10, I'm going to subtract 1 from each of these exponents. So it's going to become 10 to the 0th, and 10 to the negative 1, and 10 to the negative 2, and 10 to the negative 3. My handwriting is terrible and I'm so sorry. So what that basically is going to mean is I'm going to be left with 1.917. I shifted the decimal to the left. When I divided the original number by 10. All the digits are the same. They just each represent some exponent of 10 that is one less than originally. So that's the first thing. So again, what I'm doing here is I'm multiplying 19.17 times 2/10. I should clear some space again. Oops, I shouldn't have done that. Hang on a sec. I'm gonna leave this here. Okay. 20% of 19.17 equals 20 over 100 times 19.17 equals, because I can reduce this fraction again, 2 over 10 times 19.17. Now, if you remember PEMDAS, please excuse my dear Aunt Sally, that's the order of operations. That means if I am doing some if I'm evaluating some mathematical expression, I need to evaluate the pieces of it in a particular order, and this is that order: parentheses, exponents, multiplication, division, addition, subtraction. That means if there are parentheses, exponents, if there's multiplication, if there's division, if there's addition, if there's subtraction, then I need to execute each of those commands in this order. I need to do what's in the parentheses first. Then I need to work out the result of the exponents first. Then I need to work out the result of the multiplication and division next. And these are interchangeable. You can do multiplication first or division first. That's an interesting feature of these two. And the same thing here. You can do addition first or subtraction first, whichever you prefer. But this has to come first, second, third, and then fourth. So like 5 squared plus 7 times 3 divided by 2 plus 1 minus 4. So first I have to solve what's in the parentheses, and first I have to do the exponent part, so that becomes 25 plus 7 times 3 divided by 2 plus 1 minus 4. Now I have to do the plus 7 part, so that's 32 times 3 divided by 2 plus 1 minus 4. Now I have to do the multiplication and or division. So here is where that is. That's this 32 times the 3 divided by the 2. Now because these are interchangeable, I could do 32 divided by 2 times 3 if I prefer. I actually would like to do that because it's easier for me to think about it. If I do the 32 divided by 2 first, that's a simpler number for me to work with. That becomes 16. 16 times 3 then becomes, so 10 times 3 plus 6 times 3, that's 30, plus 3 times 6 is 18, that's 48. That's becomes, alright, I did all that in my head, so it's just because I'm running out of room. So that becomes 48 plus 1 minus 4. Now again, I could do the plus 1 first, or I could do the minus 4 first, whichever I rather. I could even do 1 minus 4 first and get negative 3, and then add that to 48 if I want. Or I could do 48 plus 1 minus 4, or I could do 48 minus 4 plus 1, because these operations are happening on the same level, addition and subtraction. So I'm going to do, it's just, again, easier for me personally to think about 48 minus 4, because it's just 8 minus, I know that 8 is 4 times 2, so it's just easier for me to think about. So that's 44 plus 1 is 45, so that's the answer. But anyway, the point of all of that I was trying to make is really the fact that multiplication and division happen on the same level. So right here, I could divide by 10 and then multiply by 2. I don't have to multiply by 2 first. I can divide by 10 first if I want, and I do want to, because it's a lot easier for me to think about conceptually, because of what we figured out over here. Dividing by 10, all that is moving the decimal place over 1. That's all I have to do. I don't even have to think about it whatsoever. So that becomes 2 times 1.917. Now, if I'm at a restaurant and I'm calculating tip, I don't need to be perfectly exact. If I'm pretty darn close, that's good enough. And because I'm a people pleaser, I prefer to give more than 20% rather than less if I have to do one or the other. So I'm going to round this number up. That'll be the quick and dirty and easiest way for me to do it. So 1.9, this rounds up to 2. So this is 2 times 2. So that's 4. So the tip then, the 20% tip, which is it's just a slight smidge bigger than 20% really, is 4. If I really wanted to actually find the exact number, alright, we could do that too. Then we do, actually it's been a long time since I've done this, but let's see. 14, carry the 1, 2 times 1 is 2, plus the 1 that's carried is 3, then 2 times, that's 18, so carry the 1, 2 times 2 is 2, plus the carried 1 is 3. Did I do that right? Is that right? Yeah, that makes sense to me, because this is slightly less than 2, so the result should be slightly less than 2 times 2, which it is. 3.834 is slightly less than 4, so that makes sense to me. So anyway, that is that. And while I'm at it, I know this was already a huge amount of material, so if you want to stop here, then by all means do so. But I want to kind of talk about binary too, because now that we've built up all this foundation, it should be easy to talk about binary. Before I do that though, I'll say one more thing about our number system being a base 10 system. Base 10 means that every place in the number is some power of 10. Oops. But it also means one other thing, which is that there are 10 possible digits that can be put in each place. Those are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 10 possible digits, any of which can be in any placement in a number in our number system. And notice that there's 10 of them and the highest one is 9. So whatever the number of digits are in the number system, the last one is always going to be the number of them minus 1, because you start at 0, not at 1. I hope that made sense. If not, let me try one more time to explain that. Because you're counting from 0, so this is the first, this is the second, this is the third, this is the fourth, this is the fifth, this is the sixth, this is the seventh, this is the eighth, this is the ninth, this is the 10th. So you'll notice a pattern, which is that whichever number of digit it is, like this is the 6th, that's always one more than whatever the digit is. This is the 5th. Number 4 is the 5th digit. Number 3 is the 4th digit, etc. That's because you're starting from 0, not starting from 1. If we were starting from 1, then the first digit would be 1, the second digit would be 2, the third digit would be 3, the fourth digit would be 4, and etc. So they would line up. The 9th digit would be 9 if we started from 1, but we don't. We start from 0. So just an interesting thing to note. And that's something that comes up in computer science a lot, because a lot of things start counting from 0, so, but it's actually, the value is actually one higher than that, but the placement is actually one less than that, so that can take like some concentration to keep in mind. That'll make more sense with an example, which maybe will come later, I don't know. Anyway, so it's a base 10 system, so there are 10 possible digits, and each number place in the number expresses some power of 10. So binary functions exactly the same as our number system, except that it's a base 2 system, which means there are 2 possible digits, 1 and 2, and each place in the number expresses some power of 2. So I'm going to write a binary number right now. You'll notice I'm only doing 1 or 0 because those are the only 2 choices I have. But just like in our number system, the exponent in the first place is 0, then the exponent in the next place to the left is 1, then the 1 over is 2. So it works exactly the same way. As you go left, the number of the exponent increases by 1, and as you go right, the same thing, the number of the exponent decreases by 1. So this is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. Sorry again for my handwriting and the spatial issues here. I forgot to put the little negative sign, my bad. Negative, negative, negative. So, what would this end up being? So 2 to the 7th, that's 2 times 2 times 2. I should have, I don't think I can do this in my head, so I'm going to make this easier for myself. I'm just going to make this easier for myself as we begin here. Yeah, let me make this 2, 3. Let's just do that. Oh, I messed up. Alright. 2 to the negative 3rd. Alright, 2 to the 5th. I'm going to just say it out loud because my hand's cramping from writing it. 2 to the 5th, that's 2 times 2 times 2 times 2 times 2. That's 2, 4, 8, 16, 32. Plus 2 to the fourth. 2 times 2 is 4, times 2 is 8, times 2 is 16. Plus 2 to the third, that's 2 times 2 is 4, times 2 is 8. Plus 2 to the second, that's 2 times 2 is 4. Plus 2 to the first, that's 2. Plus 2 to the 0th, that's 1. Plus 2 to the negative first, that's 1/2. Plus 2 to the negative second, that's 1/4. Plus 2 to the negative third, that's 1/8. And again, see, there's a relationship here, and here, and here. It's just, instead of being 8, it's 1/8. Instead of being 4, it's 1/4. Instead of being 2, it's 1/2. So, as you continue to go to the right, the number, it's like the number is the same, but it's in the denominator of a fraction now, because you're dividing it instead of multiplying it. So, anyway, 32 plus 16 is 48, plus 8 is 56, plus 4 is 60, plus 2 is 62, plus 1 is 63, plus 1/2 is 63.5. Alright, this is going to be hard for me, because we have to combine fractions now. Plus 1/2, plus 1/4. In order for us to combine fractions, they need to have a common denominator. Then we can add their numerators. So, because I know that I can manipulate fractions, and the value is the same, because what matters is the relationship between the numerator and the denominator. As long as that relationship is the same, the value of the fraction is the same. So if I multiply both the numerator and the denominator of a fraction by the same number, it has the same value. And in order to combine these, I need them to have the same denominator. So I'm going to turn this, I'm going to multiply this, both the numerator and the denominator here, by 4 to get 8. Because this is the, I can just tell in my head, I don't remember offhand, but there is a method for this. But I just know that I can make all these fractions be in a form where 8 is the denominator. It's there's a name for that, it's the least common denominator. If I want to combine fractions, I want to get them in the form of the least common denominator. That's the smallest possible number I can have be in the denominator for them that is common among them. And there is a method for achieving that, which I actually can't recall right now, but these are easy enough to work with. So I'll multiply both of these numbers by 4, and I'll get 4/8 plus, and then I multiply these two by 2, so I get 2/8 plus 1/8. That's 4 plus 2 plus 1, that's 7, so this is 7/8. And I can't reduce that, so I just have to leave it like that. So this 63 plus 7/8, that's 63 and 7/8. So basically what that means, this is in our base 10 number system. That's what I've done. What I did was I took this number expressed in binary, a base 2 system, and I converted it into a base 10 number, a number that can exist in our number system. That's what I just did. So this number written in binary has this value in our number system. And one of the reasons binary is important is it's used in computer science, because computers are based on things being in one of two states, either on or off, true or false, which you can express with a 1 or 0. 0 is off or false, 1 is on or true. So that has a lot of utility, and there's a lot to say on that, and that would be a huge undertaking, which I'm not going to do here, but yeah, there's a lot of utility for that in computer science, but it's useful to be able to convert numbers expressed in binary in our number system and vice versa. Anyway, thanks for listening to me pontificate about this, I am going to stop now. And I hope you all have a wonderful rest of your days or evenings.